I'm Aitor Arrieta, and I have been working on cyber-physical systems testing since I did my PhD. So here I'm going to introduce a bit our recent works on what we have been conducted in testing 3 generations of cyber-physical systems. Why 3 generations? Because these kind of systems have evolved, and so I'm going to start introducing a bit what I consider the first, second, and third generation of cyber-physical systems. So the first generation of cyber-physical systems are those that they don't have AI embedded. And it looks like it's not fancy anymore, but these are like 99% of cyber-physical systems that we use in our daily lives. And these include elevators. This is one of the case studies that I will later introduce because I work a lot with Orona, that is one of the largest elevators companies worldwide. Different safety critical systems like airplanes or the airbag system of our cars. The more simpler systems like an air conditioning or systems like what we saw yesterday, the drones. Even the drones, despite looking like very fancy, they usually don't have AI. Some of them they have, but the basic ones they don't. How do they look, these systems? So in the end, the goal of a cyber-physical system is to control some physical process. How? Through software, but the API between the physical system and the software are usually sensors and actuators. So basically, the user provides some reference command that can be more high level or low level. Through actuators, we kind of change the physical system, and by sensing these physical properties, we later adapt the software system makes some control strategies to adapt the physical system through actuators in a constant loop. So there are different algorithms to control these systems. Usually the lowest level ones are based on basic and old control engineering algorithms, such as proportional integral derivative controllers. Whereas the highest level control, where we have the intelligence, are more programmed through state charts or directly also code, right? This is more or less what we see in most of the cyber-physical systems that we see outside and so on. But there is a second generation of cyber-physical systems. What happened here? That the advances on AI, they permitted to make new applications of cyber-physical systems and have systems like autonomous vehicles or autonomous mobile robots like this one that is being tested by Uber to deliver food. If we go back to how these systems look like, the typical state chart is usually changed by a neural network. Okay, we can have neural networks of different complexities, and the group of Paulo has worked a lot in this aspect. Still, we need the integration with other software systems and other software algorithms. For instance, the PID controls, the ones that in a self-driving car, for instance, control which should be the speed, the final speed of each of the wheels, will still be PID controls, because these are control algorithms that don't hallucinate, and they have been very reliable. But we are now seeing a third generation of cyber-physical systems that integrate, instead of normal or more popular AI techniques, generative ones. So, and here we see these are mostly, the applications of these are mostly general purpose robotic systems. We have here one spin-off of Google that they have this robot that we will show later some simulations of them, and the well-known Optimus robot from Tesla. What it changes here? So rather than of course, the type of neural network changes, but the main difference here is that instead of having some reference commands, what we have is some instructions in natural language. So it is like R2D2 in Star Wars, where we can tell them like clean up our room or whatever, and they are supposed to do this. All these systems have certain common challenges. The first one is that they need simulation-based testing to be tested. Why? Because in the end, in this action loop that we have between the control actuators, the reading from sensors and back to acting on the system, one action that the system takes may affect the physical system, and when coming back, that adaptation needs to be considered, and in the end, the test needs to be conducted at system level and using simulation. This has two core problems. The first one is the high test execution time, because these simulators usually model complex mathematical systems to simulate the physical processes. And the problem is to flaky tests. Why? Because many of these systems are based on raw systems. Even the system under test, and now especially with generative AI techniques, they are stochastics, or in the case of these elevators, they also have sometimes genetic algorithms and so on. And the second common challenge is the huge search space. The test inputs, by definition, they have a huge search space compared to, for instance, unit testing. In this case, we have a third dimension, which is the time, because we might want for instance, a cruise controller to go first at 100 kilometers per hour, but later, after a couple of seconds, change it to 120, and so on, right? And on the other hand, we have the environment uncertainty. These systems don't work in isolation. They work in an environment where we have, for instance, in the context of autonomous vehicles, pedestrians, the lighting conditions are different, and so on. So it's not only the reference command what needs to be changed, but also the environmental uncertainty needs to be considered. Good. Recent works that we have conducted in the context of the first generation, we have published a paper, for instance, on the test oracle problem, where we propose a DSL. We have done a lot of work on search-based testing, and lastly, it's quite futuristic for me, and I haven't entered in much detail, but we have also applied quantum computing to model, for instance, test oracles in the context of elevator systems. This work was done with collaborators from Simula and National Institute of Informatics in Japan. But into today's work, because I cannot speak about everything, I will talk about this work accepted at MC, where we apply a technique that was developed here together with Paolo into the context of elevator systems. Why I want to talk about this one? First one is because I really liked this paper. Secondly, because industry was involved, the problem was identified with them, and we involved them in the evaluation and so on. And secondly, because since I am at UC, then I wanted to talk about this. The industrial case study that we used is the traffic master of elevators. So this system, basically what it does is when we call an elevator, we say, okay, I want to go upstairs or whatever. All this different data is communicated to the dispatching algorithm, okay, through a CAN network. Not only the different calls that are activated are provided, but also information about each of the elevators. Like, okay, this elevator is in this position, it is full, this one is already where the call was made, and so on. And after computing some complex algorithm, the elevator assigns the dispatching algorithm assigns the elevator to the passenger. So for instance, here, because this one is with the doors open and one person inside, already this one is the most optimal one. Okay, how do this Orona, the company that is involved here, test these systems? So it uses a simulator in which we have two inputs. The first one is the test input, that is a set of passengers traveling through the building with different data, such as at what time they arrived, which is the mass of the person, and so on and so forth. Okay, and on the other hand, we have the building configuration. Each building, by definition, is different. Some have 4 elevators, others have 2. The number of floors is different. Each elevator can handle more passengers or less passengers, and so on. So based on this, we simulate this in Elevate, which is the standard elevator. You can see that it doesn't look very fancy, the simulator, but it is the elevator that all companies use. And as an output, based on these inputs, they provide different simulations results, like which has been the time that each passenger had to wait, which has been the average waiting time of all passengers, different domain-specific quality of service metrics, and aspects like energy consumption and so on, which is now important. So some key problems that we have here, as I commented, the search space is large and multidimensional. We have, for instance, in this particular case study, we had an entire day of people traveling through elevators inside a building in some offices of Madrid. Both the passenger data as well as the installation was real, right? So first of all, we have a huge amount of data, whereas the failure can happen in one specific time window during the day. And on the other hand, when generating test inputs using search-based techniques, we figured out that eventually we could generate unrealistic or invalid test inputs. That is, we can find specific cases where physically the system of elevators, it's impossible to give an appropriate quality of service because there are many passengers, or because when all elevators were here, we called from another floor that it was far from the elevators, and so on and so forth. So, inspired by Deep Janus, which was developed by Vincenzo Ricci under the supervision of Paolo, we proposed Lift Janus, an inspiration of it. But we made some modifications. The first one was to reduce the test input to the minimal size until a low quality of service was provided. This way, we could reduce, on the one hand, the search space, and on the other hand, the test execution time. Based on this, we applied a search algorithm that instead of generating single inputs, it generated pairs of test inputs. So here we will have two members where we try to minimize as much as possible the distance between them. For instance, changing the mass of one passenger from 75 kilos to 80 kilos. This is a minor change that should not affect the system. But at the same time, we try to maximize the difference in the quality of service of each of these two test inputs, right? And on the other hand, what we try to do is also to diversify the distance between this one and this one. For instance, it is not interesting that we only move the mass of one specific passenger, but maybe we are also interested in on mutating the mass of a passenger in that comes minutes later, right? And this way, what we tried to do is to maximize the diversity of faults and failures. So once we do this and we obtain different members, what we launch is a automated misconfiguration repair algorithm. Why? Not only to repair the system itself, but to ensure that what we have generated makes sense and it is a valid input. And if it is somehow repaired, we provide this to the set of the valid inputs. If it doesn't, then we provide a manual assessment that checks whether this has been repaired or not. So yeah, we evaluated this into two different real test inputs that we obtained from a real installation. Here are some results. As you see, our algorithm is able to change here to maximize a lot the difference in the longest waiting time between two different members. Here we have the baseline approach that it takes the same algorithm, but we make one minor modification in order not to be guided. And in green, we have the same algorithm, but without the preprocessed delta debugging test input. So here, for instance, we see that eventually it passes the baseline algorithm, but it takes much more time to compare. And here we see, for instance, that our algorithm is capable of providing high difference, longest waiting time differences with minimal distance, whereas the search algorithm, the unguided approach, it doesn't. Of course, reviewers asked for more baselines, so we included some more state-of-the-art techniques, but still our approach was better. And here we have some results of okay. Yes, we provide this, but are these test inputs really valid? So after applying the misconfiguration repair algorithm, we see that the longest waiting time differences between different members were decreased a lot. Okay, so this is the first work that we did in the first generation of cyber-physical systems. As main conclusions, in the end, we saw that the successful adoption of state-of-the-art techniques, it was a successful adoption of a state-of-the-art technique to an industrial case study system. But also we found that in the end, to a technique like this to be scalable, it needs the combination of techniques. Here we combine delta debugging, search-based test input generation, and misconfiguration repair. So yeah, and we also validated this with engineers from Norton, and they were quite happy actually. As for the second generation of cyber-physical systems, here are some recent work that we recently published. The first one at Safe Track this year, a collaboration with PAL Robotics, and the second one on using multi-objective reinforcement learning for critical scenario generation on autonomous vehicles. But today's work, more than testing, it's on monitoring. I'm going to present Marmot, where we adapt metamorphic testing to runtime monitoring. Here, we don't use a previous Paolo's work, but we use it as a baseline. So, yeah. So basically, before Marmot existed, there were two main techniques. One was based on autoencoders, where based on an image, they try to reconstruct an image, and later they check whether the reconstructed image is similar to the previous one. Here we have examples of Self-Oracle that was led by Paolo, DeepWard, and so on. And on the other hand, also was led by Paolo, we had some approaches based on explainability, where based on attention maps, they obtain some confidence, and yeah, based on this, they predict some failures. Example is Third Eye, published at ASC. So the first one, it has some limitations because they are oriented only to detect failures that are related to out of distribution data, and they omit aspects like faults related to the architecture of the system itself and so on. Whereas the second one, they don't have this problem, but they are expensive to execute because they need to execute multiple times the system and so on. So instead of this, we proposed Marmot. The idea here was, okay, we have an input image where we generate based on an input relation and a follow-up image. For instance, we can put in black and white this one, and we execute twice the neural network with both images. So with this, we obtain two different actions, the real action and the follow-up one. And here, if these ones are different, after conducting some time series analysis, we check whether there is a failure or not. So the approach is pretty simple, and most of the work is an evaluation. We did this evaluation with a real mobile robot. Of course, reviewers said that this wasn't enough, so we complemented it with some dataset that Andrea Stocco provided us, and we compared it with Self-Oracle and also more general approaches for measuring uncertainty, like ensemble or MC dropout. So as some highlights of the evaluation with the Le rover, we applied different type of anomalies. Internal anomalies, where we changed the internal structure of the system, of the neural network. Here, Marmot outperformed all the baselines. Some external anomalies that were also based, for instance, on having adding some noise in the input or whatever. Here, Marmot also dominated in most of the metamorphic relations, because we compared 5. Dominated the baseline techniques. And some external filter-based technique, where we used different circuits here. In the first one, Marmot was best, whereas in the second, Ensemble. And in the case of the second use case, one of the metamorphic relations of Marmot outperformed the remaining algorithms in one of the when we included internal anomalies. And when applying external anomalies here, Self-Oracle, one of the configurations of Self-Oracles was best, followed by Marmot. But Marmot was still competitive. So in most of the cases, Marmot, that is a pretty simple technique, outperformed the rest of the baselines, while in some of the cases achieving comparable results. So here the interesting part also is how much time before the failure occurs can the system predict that a failure is going to occur. So here we see different cases. The most interesting ones for me is these ones because they converge somehow some frames before. But yeah, we have like different mixed results. For instance, here we see that variational autoencoder perform quite competitively. So as conclusion here, Marmot, in the end, what we did was apply a well-known technique of testing to runtime monitoring, which I think that it was quite exciting. And it overcomes some limitations. So now let's go to the fanciest one, the third generation of cyber physical systems. So in this case, what we have are generalistic robots, which are capable of performing diverse open-ended tasks with minimal instructions. Here is the well-known example of Tesla. Later, I will put some video of this one because it's quite funny. They understand and execute high-level commands, and they use in the end dexterous manipulations to achieve this. Behind these robots, we have the technologies that is based on visual language action models, and here is the typical architecture of one of them. Basically, what they do is they have as a backbone one visual language model, which takes both images as well as one input prompt based with different tokens. This high-level visual language model is the one which strategically says how the system should move. This is here it has like the high-level intelligence. This also is executed more slowly than this one. And the second one is the diffusion transformer, which is a diffusion model that converts different tokens provided by the VLM, as well as some noise tokens that come from the actions. Here there is a feedback loop, okay, into actions that smoothly move the different robotic arms to their objectives. So here we have identified several problems, and we have started targeting the first one, which is the test oracle problem. In the end, in traditional cyber physical systems, the requirements are somehow static, fixed. We define them in the beginning of the development process, and later we can easily encode them. Okay. Later we can also use different transformation, different signal temporal logic strategies or other kind of strategies to convert them into mathematical equations that can guide us to, for instance, guide the search-based test input generation. But we do it once. Okay. Here is one example of requirements from an industrial case study. The problem with this third generation of cyber physical systems with VLAs is that the requirements change depending on which is the instruction prompt. Here we have one example of the previous robot that I showed you, of the one from the Google robot, where we say, okay, pick up the apple, and the robot directly picks the apple. Which are the current oracles that these robotics people researching this in the robotics community use? These oracles are named, or I name them somehow symbolic oracles. So for the pickup apple, basically they have a domain-specific language where they say that the final goal is that the agent should be holding the apple. So we have here at the end of the simulation, the apple is with the within the agent is holding the apple. So the test would be passed, right? Okay, but let's go now to another example. Here we have, instead of pick up the Pepsi can, we have the pick up the sorry, instead of having the pick up the apple, we have the pick up Pepsi can. And in the end, somehow it ends up picking up. That's right. So we would have here a pass. Of course, we can generate this kind of oracles with an LLM, but here you see that the quality of the task execution is not the same. And the can drops several times before it finally manages to pick up. Okay. Here we have another example of the Groten 1.5. That is with a humanoid robot. The goal is to move the bottle to the cabinet. And you can see that in the beginning, it doesn't move to the cabinet, but later when closing the door, it ends up inside. Of course, this test case was labeled as pass. And here I had a huge a huge discussion with Lionel some weeks ago in Shonan, because he said it is a pass. The goal is finally finished. Yes, but it is not as a human would expect that a humanoid robot would do this task. Okay, so somehow these oracles fail to capture the quality of the task execution. They are unable to, for instance, caption also trajectory optimality. And in my opinion, that was a false negative, because, okay, it ended up inside the cabinet, but this is not how we expect these systems to do their tasks. Automation is only possible for some predefined templates. This is, we can add, okay, pick up, and based on the objects that we have in the environment, generate the test inputs, and based on this, we can use the symbolic oracles. We can also eventually use an LLM, but we also know that they hallucinate. So yeah, in the end, we have the test oracle problem in this area too. And lastly, these oracles are only limited to simple tasks. Currently, these VLAs are still in their infancy, but eventually we expect them to do different tasks, right? So our first attempt to target this problem was to evaluate, on the one hand, uncertainty based on we thought that those cases where the uncertainty is higher, the quality of the task execution should be lower, right? So to measure uncertainty, we do it in two different ways. On the one hand, we measure the uncertainty of the VLM itself. So this connection is based on some tokens, and based on the tokens, we can define different uncertainty metrics, like we can use Deep Genie or the maximum probability or whatever. And on the other hand, we also measure the uncertainty at the outcome of this diffusion transformer model. Here, for instance, we have some metrics where if at some inference times, because the output of this of these models are for which should be the position of the robotic hands, right? So if at one inference time we have this position, but in the following one we have this one, but in the afterwards we have again the same one. Here there is some sort of uncertainty that the model doesn't really know where should the robotic hand move, right? And besides this, we define different quality metrics. For instance, if we know which are the target objects, we can easily identify which is the optimal path there. So based on this, what we did was execute many tasks. We obtained only the successful ones. We obtained 900 successful ones, and we manually labeled by defining some criteria of what is a high quality, low quality, or medium quality task. We define which is the quality level of each of these of these simulations. Based on this, we assess the correlation, and also we assess the discrimination capabilities of different metrics with respect to successful and unsuccessful tasks. So the findings here were that in the end, success rate alone was not suitable for assessing the quality metrics of BLA models, and this is the standard metric that the robotics community are using. But we saw that very successful robots, they perform tasks with very low quality. We saw also moderate to high correlation between some of the proposed uncertainty and quality metrics and the human perceived quality. So here we have some nice finding. And most metrics showed some discrimination between successful and not successful tasks. But we also found that those that were low quality, the discrimination was not that much. So in the end, our metrics would classify those successful tasks of low quality as unsuccessful. So this was the first attempt that we did. The second attempt, as I really like metamorphic testing, what I wanted to do is try this with metamorphic testing. So basically, we defined here two different metamorphic relation input patterns. The first one was the trajectory consistency pattern. These are any kind of input transformations that should not affect the trajectory of the robot. For instance, a simple one. If we have a synonym, instead of pick the Coke can, we say grab the Coke can, the trajectory should be the same, because in the end we are asking the same to the model. We can define this at different levels. We can, for instance, change the illumination of the stand. We can add one object in one place that doesn't interfere with the trajectory, and so on and so forth. And on the other hand, we have the contrary. We have the trajectory variation pattern, which defines any transformations that should affect the trajectories. For instance, if we ask not to pick up the Coke can, it should either not move or pick another object in the workspace, right? So here we have some early results. These results were just are taken out of the oven yesterday. Here we have we changed the pick the sponge for take the sponge, and you can see that this change made the robot be unsuccessful in the follow-up execution, right? And this was detected with this. Here is another one with the same exact transformation, because still we are, sorry, not this one. Here we have on the one hand pick the Pepsi can. Here it takes it very well in the first try. Whereas here it happens this. So the variation in the trajectory is huge, right? So yeah, we are working in this technique more in depthly. So to finish this presentation, some future research avenues that I would like to mention within the first generation, even if they look like very old-fashioned cyber physical systems, these are the cyber physical systems that we see most, and many of them will still continue not to integrate AI. But here, for instance, test flakiness is something that has not been researched a lot. I think that there might be here, when we have test flakiness, debugging this kind of bugs is very difficult. So I think that we can provide approaches in which we can be able to consistently trigger these failures, or given a flaky failing test input, we can make it somehow non-flaky. For instance, we have explored here delta debugging for this aspect. And for instance, automated program repair is a problem that has been largely explored in the in the community, but not that much in the context of cyber physical systems. Here the challenges are very hard because the test execution time to validate one specific patch is huge. So it's not easy. But in any case, this is a problem that is very interesting. In the context of the second generation of cyber physical systems, recently a lot of work has been done, but some problems are the same as the first generation of cyber physical systems, and can even be more exacerbated. For instance, the fault localization, whether the bug is coming from code or from AI, is something that has not been solved. And still, we will have common software running along with this, because still we will have these PIDs and so on. So I think that the techniques should look for integration of both the code itself, but also the AI techniques. And in the third generation, in this case, this field is still in its infancy. A lot of work is being done by the AI and the robotics communities. Every day there are 1 or 2 new papers on archive. So it is crazy how they are advancing this. But the current benchmark that they use are largely non-systematic. They are using the same benchmarks with the same tasks, and they largely depend on binary success rates that we found that they are problematic when assessing the quality. In this case, I think that the test oracle problem is something to be targeted. The problems that I mentioned with binary test oracles, but also still these VLAs are somehow stupid. They are not able to solve also simple tasks, but eventually they will become more complex, and instead of having pick and place like tasks, we will ask them to, for instance, make the coffee, where, for instance, there we will have different subtasks, and the test oracle problem there will be exacerbated. Metamorphic testing is an alternative, but we think that it's going to be complementary. Not all failures will be able to be caught with metamorphic testing. And in the context of test generation, here we have also identified several problems. Here, in this case, the problem is not single modal, it's multimodal. We have the environment itself, but also some prompts with text. The test adequacy is also not evident. White box approaches like the neuron coverage and so on, we have found that are problematic. I think that I advocate here for some novel black box adequacy criteria. And we should not forget the safety and security of these models. In the end, this will work. This will be integrated with ourselves, and this is an important aspect. To finish, here is some video of the Tesla Optimus robot. The funny part here is that Elon Musk saying that it is AI what it has, but if you see here, you can see that there is somehow someone removing the glasses. So I don't know if we can trust that this is really AI. Recently, yeah, you can see that eventually they are somehow. So yeah, later it looks like it loses the connection or something, and it directly falls. So yeah, in this context, I already announced before we'll have a new lab member soon. So here, if you have any ideas or even collaborations, we are more than welcome. Acknowledge to all the collaborators. Thank you very much all for attending, and yeah.